Hey everyone, I'm going to go over the Zoom for homework 8, chapter 9 and 10, which is all energy, power, and work. So we'll kind of go through like we normally do and talk about concepts and equations and all that good stuff. So in our first problem, we have a box that's sliding across a floor, and it's brought to a halt after traveling a distance of 55 centimeters. The force that was pulling on it was 16 newtons. So if we understand kind of first of all what, oh shoot, my sorry, I had to plug in my tablet. Okay, so first of all, we have this concept that work is F dot D. What that means is the force times the distance. It's a dot product, and when you dot two vectors, what you get is the magnitude of A times the magnitude of B times cosine of theta, which is the angle between A and B. We'll talk more about that in a later problem, but for now, what that means is that the work is negative if F and D are opposite, or the work is positive if F and D are in the same direction. And if F and D are at some angle, then the work is obviously F times D times the cosine, the component along the angle between them. We'll talk about that a little bit later, as I said. But work and energy are related by the work is also the change in kinetic energy. So what you get here is you get F dotted with D is mv final squared over 2 minus mv initial squared over 2. And that is a scalar. That will be joules or Newton meters. And so when we look at our first problem, what it's telling us is that there's a 25 kilogram box. It's sliding to the left, and it's brought to a halt in some distance D, which turns out to be 55 centimeters. And the rope that's doing that has to have a force of 16 newtons. So what you can imagine is this box is initially some loose rope attached to it. It's traveling with some velocity initial, and after it travels a distance D is 0.55 meters, and the force of tension is 16 newtons, it comes to rest. During this trip, the distance, the force is this way and the distance is this way. Since those two vectors are opposite of each other, the work, which is F dot D, which will be negative F times D, is going to be equal to mv final squared over 2 minus mv initial squared over 2. But we know that this is 0 because it's going to come to rest. So we know that work will be negative. That work is simply 16 times 0.55 with a negative sign on it in joules. 16 times 0.55 is 8.8 joules of energy. The negative sign implies that it lost 8.8 joules of kinetic energy as it came to rest. So negative 8.8 joules is how much work was done by that tension force of the rope. How much work was done by gravity? Now, gravity, while this thing is sliding a distance D, but gravity is the weight or mg, down. And if we look at these two, d points this way and mg points down in the negative y, and this would be in the x, and the angle between them is 90 degrees, or negative 90 degrees, actually. The work, again, is F times D times cosine of the angle between them. And 90 degrees, cosine of 90 degrees is 0. So gravity can do no work in this case. Gravity does no work in stopping our block as it slides to rest. And that's why it's 0. All right. You throw a 5.5 gram coin straight down at 4 meters per second from a 75 meter high bridge. So now we're going to have a 75 meter high bridge. The mass of our coin is 5.5 grams, or 0.055 kilograms. And we're going to throw it with an initial velocity downward of 4 meters per second. Okay, so work, again, is force times distance. And as it falls, and it covers a distance of 75 meters, our force is also in the same direction as D. D is down, our force of gravity is down, which is mg. And the work done by gravity, in this case, is going to be the force of gravity times the distance that it falls, times cosine of the angle, but they're in the same direction. So the angle between them is 0. Cosine of 0 is 1. So this is going to be mg times d, or the height. So this will be 0.0055, 9.8, and 75. The work is positive. And it's positive because the force and the distance are in the same direction. As the coin travels downward, it is traveling in the same direction as the force of gravity, and therefore positive work. So 0.0055 times 9.8 times 75 is 4.0425 joules. So 4.04 joules. Or 4.0, I guess they're only using 2 sig figs because that's all they gave us here. So 4.0 joules. It is positive. Basically, gravity is increasing the kinetic energy. It's speeding up the coin as it falls down. Had it been traveling upward, gravity would have done negative work and its kinetic energy would have decreased and it would have slowed down until eventually reaching the top. At what speed does the coin hit the water? Now, we know that the work done was 4.0 joules. Actually, we should probably go back and use 4.404 joules. And that work is equal to the change in kinetic energy. Okay. Now, the initial velocity was 4 meters per second squared. But that initial was downward, so we need to say it's negative. Okay. Does it matter? No, because it's going to be squared. Okay. However, if we want to find V final, mv final squared over 2 is equal to 4.04 joules plus mv initial squared over 2. Divide through by 2 over m. So these go away, and then take the square root of that answer. And we can do a little bit of cleanup here. V final will be 2 over 0.0055, 2 over the mass, times 4.04 plus 0.0055 over 2 times 4 squared. Now, you could actually clean this up a little bit more if you wanted, and you would get 2 over m times 4.04 plus the initial squared. The 2m would cancel, Doesn't matter which way you want to do it. I just plug it in as is. So 2 divided by 0.0055 times 4.04 plus 2 divided by 0.0055 times 16, and then take the square root of that answer. 2 divided by 0.0055. Sorry, 2 divided by 0.0055 times 4.04 plus 2 divided by 0.0055 times 16. And I don't know why this is being so weird. It's being very weird. It's giving me weird answers right now. Oh, right. I'm being odd. All right. So 8.08 divided by 0.055 plus 16 is y. I'm doing something odd with my oh, I see. I see what they forgot. They forgot. Therefore, right there. So let's go back for a minute. I'm going to do this. The work was mgh, and that is mv final squared over 2 minus mv initial squared over 2, multiplied through by 2 over m, and you get 2gh times v final squared minus v initial squared. Or v final is the square root of v initial squared plus 2gh. That is 4 squared plus 2 times 9.8 times 75, which is 16 plus 2 times 9.8 times 75. Square root of that answer is 38.5 meters per second, or 39 meters per second. What did I do weird here? I'm not sure. So it would be 8.08 divided by 0.055 plus 16 and the square root. I was just being weird. It worked out. I was doing something odd with my calculator. So 38.5, it's technically downward. However, they asked us for speed, so we just need the speed. And that's it. Just remember that your work is the change in kinetic energy, and you can solve this for V final, which is what we wanted to do, which happily gives us back the what we used to use as a we used to note that this was the same equation that we got for whatchamacallit, for free fall. Remember, free fall was V final squared minus V initial squared is equal to 2G Y final minus Y initial with a negative sign, but H is Y initial minus Y final. So when it falls, this would be the height minus 0, and therefore that would be H. Anyway, Not bad. If you can not screw up your calculator. Okay, so first of all, we have 3 pairs of vectors and we're going to evaluate the dot products. Now they've given us the magnitudes. They have not, except in this case, given us the angle between them. And whenever you take a dot product, A dot B, you first put them tail to tail, A and B. So in order to either cross or dot or cross, whenever you multiply vectors, you place them tail to tail and you find the angle between them, whatever that angle is. We measure angles positively from the x-axis, so this would be some positive angle. But what we get is that A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. We'll see what these are here. So in this first case, we're going to evaluate the dot products of this A and this B. And they've given us everything. This is 3, this is 4, magnitude of A is 3, magnitude of B is 4, and the angle between them is 130 degrees. So in this case, it would be 3 times 4 times cosine of 130 degrees. All right. 12 cosine of 130. 12 cosine of 130 is negative 7.7. I'm sorry, 7.7. I don't know how to write. I don't know what the units are. There are no units given. So negative 7.7. For this one, we need to put C and D tail to tail. D points this way, C points this way. And then we notice that the angle between them will be 180 degrees. So placing them tail to tail, 5 times 4 is 20 times cosine of 180 gives us a negative sign. When they're in opposite directions, when you place them tail to tail and you get opposite directions, you get a negative sign, negative 20. Here, we need to place these E and F tail to tail. And now we need to do a little bit of geometry because we know that when we put them this way, F is 4, but E is 5. Now, originally, they had E here, and this was 130 degrees. This whole thing is 180, so this is 180 minus 130, or 50 degrees. This angle is 50, this angle is 130. Together, from positive x-axis to negative x-axis gives you 180 degrees. So E dot F is 5 times 4 times cosine of 50. We can already see that this is going to be in that direction, but 20 cosine of 50 is 12.8 or 13. They want 2 sig figs. So this answer is 13. Okay. But the big trick is place them tail to tail. E and F have to be tail to tail for you to do a dot product. And that's all. I just wanted you guys to have a little bit more practice with dot products. Okay. Now, normally when we do energy, by conservation of energy, we note that the energy is mgh plus mv squared over 2. And then we set that energy, we pick 3 or 4 different places. This, however, is the gravitational potential energy. If there's a spring, and this is the kinetic, then we also have to add this kx squared over 2 term. The potential energy of gravity is mgh. The potential energy of a spring is kx squared over 2, okay? And the work done is the negative of the change of potential energy. So the work done by gravity is mgh final mgh final minus mgh initial with a negative sign. The work done by a spring is the negative change of potential energy of a spring, and that is kx final squared over 2 minus kx initial squared over 2 with a negative sign. However, for a spring, for a block on a spring, if you didn't compress it, you didn't pull the block out, in or out, that rest length, that L, X is 0 when it's sitting at its rest length. And then if we compress it some, we would get a negative X. And if we pulled it out, we would get a positive X. The force of the spring is negative Kx. The potential energy of the spring at any time is going to be Kx squared over 2. Okay, they're related because if you integrate you take the derivative of the potential energy, you get the force. If you take the integral of the force, you get the potential energy. That's how that works. But right now, what we want to know is a horizontal spring with a spring constant, K of 950, is attached to a wall. It is compressed 5 centimeters. So we go, K is 950 newtons per meter. X initial will be 0 and X final will be negative 0.05 meters. It's compressed 5 centimeters. We compressed it 5 centimeters. What we want to know is how hard should you have to push? Well, the force is negative Kx, and K is 950, negative sign, but X is negative 0.05 because you're compressing, and the force you have to push on the spring would be 950 times 0.05, 47.5 newtons. Okay, 47.5 or 48 newtons. That's it. We're trying to understand how to calculate the spring force. It's not negative because they're pushing on the spring, and the force, technically, this is the force of the spring pushing back, so it's positive. The person pushing would actually have to push in the negative direction, but this is the force of the spring, which is why it's positive, and this is the force of the push. But they just want the magnitude of how hard it's pushing, which is pretty standard in springs. Okay. In this case, we're going to have a spring with a spring constant of 85 Newton per meter, and a 2.5 kilogram box slides across a frictionless floor, hits the spring, and compresses it 6.5 centimeters before stopping. So in this case, we have initially, take that back, the spring is sitting here at its X is 0. And there's a box that's traveling this way with some initial velocity. It's going to hit the spring and compress the spring 0.065 meters, 6.5 centimeters. So it compresses it that far before coming to a stop and then shooting back the other way. So V final will be 0. It's going to come in, press on the spring and stop, and then the spring's going to push it away. And we want to know what V initial was. The energy at any time, we don't have to worry about MGH because the height isn't changing between these two, is MGH plus KX squared over 2. Now, this is energy 1. Energy 2 is the same thing. And by conservation of energy, they are equal. So this was energy 1, this is energy 2. We set those two things equal. there's no other forces besides spring or gravity, and we don't worry about gravity. And whoops, I'm being crazy. We're ignoring gravity, but I forgot the kinetic energy. I meant to write the kinetic energy, not the gravitational energy. So now, first of all, K was 85 newtons per meter. That's the spring constant. And the mass was 2.5 kilograms. And X final, X initial, or X1, I guess I should call it. X1 was 0 meters. X2 is 0.065 meters with a negative sign. And that's all I need. Well, I actually need that at V2. V2 is 0 meters per second, and V1, I don't know. So I want to find V1. So first of all, V2 is 0. And what I get is that M V1 squared is kx2 squared over 2 minus kx1 squared over 2. Move that over. Then multiply through by 2 over m, and then take the square root, and you will get the initial velocity. So set the energies equal to each other. The energies are just the kinetic energy and the spring energy. First of all, x1 is 0 because it's not touching the spring yet. So I can actually get rid of this whole term. This term is 0 because x is 0. This term is 0 because it came to rest. Multiply by 2 over m. Now, that ends up being k over m times x2 squared. So 85 divided by 2.5 times 0.065 times 0.065, and then take the square root of this answer. And I get 0.379 meters per second, or 0.38 meters per second. All you have to do is write the energy. The energy at any time is mgh plus m v squared over 2 plus kx squared over 2. And then there's no h change. There's no height change. So you can get rid of the height. Mg plus mv squared over 2 plus kx squared over 2. And this is 1 and this is 2. There's no height change. So those terms go away. Then at 2, it came to rest. And at 1, it wasn't touching the spring. And you just set E1 equal to E2 and solve for V. That's all you have to do in these problems. They're really straightforward. I don't know what just happened there, but and our answer is 0.3. All right. Now, we're going to have to talk about, this is only true when you don't have any non-conservative forces. Conservative forces are springs and gravity, and kinetic energy is always the definition of work. So really what we're seeing is that work is the change in kinetic energy, which is equal to the negative change in potential energy of gravity and the negative change in potential energy of a spring. However, if we do have a non-conservative force, one of the things non-conservative forces do is they pull energy out. And our biggest non-conservative force is friction. Now, the force of friction, we already know, is mu times n. The work of friction is mu times n times d, where d is however far it slides. This is usually written with a negative sign in your book, but don't do that. The reason why is, in this example, we have a piece of luggage that's initially sliding with some velocity, and it comes to rest. So V final is 0. There was some work of friction done. There's no springs in this case. So let's call this energy 1 and this energy 2. Energy 1 is mgh plus mv squared over 2. Energy 2 is mgh plus mv squared over 2. 1, 1, 2, 2. Now we can set those two things equal. Energy 1 is equal to energy 2. However, we have to account for the work of friction as it slid to a stop. So it slid some distance d, and there was a work of friction, mu n d, in this range. But n, we already know, is mg. The normal force on something sitting on a horizontal surface is mg. So we need to take that energy out somehow. And the question is, we can either write this as E1 minus the work of friction is E2, because however much energy we started with, we lost a certain amount due to friction, and that left us with the energy at 2. Or we can write E1 is equal to E2 plus the work of friction. And you're going to see here that we actually prefer to do this in this case. So what happened was a 15-kilogram suitcase was sliding across the floor at 1.2 meters per second, and it comes to rest due to friction. And it slid 2.4 meters. Okay, so it slides for 2.4 meters before stopping. Now, which of these can we get rid of? Well, we don't need the height change because there is no height change between E1 and E2. And we don't need the final velocity or the final kinetic energy. This turns out to be 0. So what we get here is we get mv squared over 2 is equal to 0 plus mu mgd. This is the work of friction. Now we could have written mv1 squared over 2 minus mu mgd is 0. These two equations are the same. And what they want us to solve for is the coefficient of kinetic friction. So in this case, let's just get rid of this. We're going to divide through by mgd, and we get that mu is v1 squared over the m's cancel, 2gd, or 1.2 squared over 2 times 9.8 times 2.4. And that gives us 1.2 times 1.2 divided by 2 times 9.8 times 2.4, 0.031 is what our mu is equal to. 0.031, and they wrote it that way. I believe that was all we had to do on that one. So yeah, just understand that the work of friction always pulls energy out. Another way to see this is that the initial kinetic energy was completely used up by friction in order for it to stop. All of the kinetic energy disappeared due to friction or was taken out by the work of friction. So the kinetic energy initial has to equal the work of friction and then solve for mu. Make sure that you understand if it's on a flat surface, n is mg, which is normally the case. If it were on an incline, n would be mg cosine, which is usually the case. All right, now these ones get a little bit tricky. How much work does an elevator motor do to lift a 1,900 kilogram elevator a height of 110 meters? Okay, so remember that the work done, we want to know the work done by the elevator. So the work done by the elevator, it has to pull up with some force a weight of mg, where m is 1,900 kilograms. Okay, it has to pull that up a distance y, where y is 110 meters. And so the work done is force times d, or 1900 kilograms times 9.8, that's our mg, times 110. So 1900 times 110 times 9.8 gives me 2,048,200 joules of work. So 2 times 10 to the 6, about 2 million. How much power must be supplied if it needs to do this in 43 seconds? So in a time of 43 seconds. Power, or at least average power, is work change over time change. The work change was 2,048,200 joules. The time change was 43 seconds. Power is pretty easy to understand. I get 47,632 watts, 33 watts. And if we want to change that, that's 4.8 times 10 to the 4th watts. Yeah. And that's it. The work is mgh, and power is the work divided by time. All right. In a process in which a system's potential energy increases while the environment does work on the system, does the kinetic energy increase, decrease, or stay the same, or is there not enough information? Well, we don't know. This question I gave you because I wanted you to think about this. Yes, in general, the mechanical energy says that the energy is always some combination of potential energy and kinetic energy. As potential energy increases, kinetic energy should go down because E is conserved. However, in this process, we don't know that energy is being conserved. So even though the potential energy could increase, that doesn't mean that the kinetic energy also isn't increasing. We just don't know. It just all depends. So the answer is, who knows? Sorry. All right. This is a spring problem, and I wanted you to do this one because I want you to understand that springs, there's a variety of things that we use as springs. In this case, a plane grabbing a wire on an aircraft carrier to slow it down. Now, we assume that initially the plane has some initial, some initial velocity, and it's going to grab with its tail hook this wire. And then the wire is going to be pulled. So the wire's at x is equal to 0. Then the wire is pulled to some d, and it stops the plane. Right? The plane has some final velocity of 0. And so what we need to determine, we're told the spring constant of the wire. We're told the mass. Mass is 1.7 times 10 to the 4th kilograms. And K of the spring is 6.4 times 10 to the 4th newtons per meter. And we're told that if it stretches 33 meters, what was the landing speed? Okay, so first of all, energy 1 is equal to energy 2. This is our 1, this is our 2. Energy 1 is mv0 squared over 2. We could write kx initial squared over 2, but this is 0. And mv final squared over 2, which is 0, plus kx final squared over 2, which is our d. Okay, and so we see that we get the initial kinetic energy is again equal to the final spring energy. You can plug in d there if you want. And what we want to know was, what was the initial? Multiply through by 2 over m. and the 2 cancel and you get over m, and then take the square root. And what I get is this number, 6.4 times 10 to the 4th over 1.7 times 10 to the 4th. They're the same power, so I just need 6.4 divided by 1.7 times 33 squared. What I get there is 6.4 divided by 1.7 times 33 times 33. Don't forget your square root. I get 64 meters per second. So again, that's all you need. I don't know why someone put 6144 kilometers per hour. All right, so now we're on to our potential energy diagrams. And the only thing that you need to remember on this, a potential energy diagram has some potential energy here and then some position here. And then usually, as is the case in this one, mine is 2. So at 2, and then there's the top of the hill is at 5. So there's some top of the hill and it drops all the way down to 0. Now, mechanical energy is kinetic energy plus potential energy. And so you need some total energy, and this is A and this is B. We need some line that's total energy. So let's say we draw our line of total energy at 5 joules. These are in joules. This is our energy total. Now at A, it's going to have kinetic plus potential. At A, the potential energy is 2 joules. We can see that because that's where it is at A. So the kinetic energy would have to be 3 joules, assuming that my energy was 5 joules to begin with. And sorry, that should be A. If I'm at EB, notice my potential energy is 0 joules, so my kinetic energy would have to be 5 joules. And if I'm at, say, C is here, my potential energy would be 5 joules, and my kinetic energy would be 0. So your kinetic energy is always the difference between whatever your total energy line is and where your potential energy is. All right. So we're told the mass has a the particle has a mass of 100 grams, 0.1 kilograms. And we're asked, what is the minimum speed the particle needs at A to reach B? Now, at A, it needs to have a total energy of 5 joules, right? To get over the hill, okay? At A, it already has 2 joules. So it needs the kinetic energy at A has to equal 3 joules because when it gets to the top, it's going to reach, it's going to need to have 5 joules of potential energy. So the kinetic energy at A had better be 3 joules so that the 2 joules of potential plus the 3 joules of kinetic equals enough energy to get over this hill. Now, mVA squared over 2, the kinetic energy at A, has to equal 3. So VA squared is equal to 2 over m times 3. Take the square root, which is 6 divided by 0.1. That would be square root of 16. 7.7 meters per second. Okay. Then, what minimum speed does it need to have at B? Well, at B, all of its kinetic energy had better be equal to 5, so it can get over that hill. So mVB squared has to equal 5 joules. And again, VB is equal to 2 times 5 over m, or 10 divided by 0.1, which is 100. So this would be 10 meters per second. All of its energy has to be in kinetic energy at B, and it has to be its total energy has to be at least 5 joules in order to get over this hill to get to A. Not too bad. All right, those are 12. Oh yeah, the budget jump. All right. So in this one, we're going to have person on a spring is going to get launched down, and then it's going to go up an incline that has friction. So what we want to know is, first of all, we need to look at this in a couple different ways. We need to choose some positions for our, this is where our hill is. Initially, we're on the spring, and then the spring's going to come to rest at some point. So this is X initial is whatever, and we're here. So this will be our energy 1. Once it clears the spring, it'll be energy 2. And when it gets to the bottom, that'll be energy 3. And then when it gets to the top of the ramp where you come to rest, I believe, will be our energy 4. Now, let's first of all deal with energy 1, 2, and 3. All you have to do is write the energy, mgh, mv squared over 2 plus kx squared over 2. mgh, mgh, mv squared over 2, mv squared over 2. And then we're going to start getting rid of stuff that we know it doesn't have. Since there's no friction between 1 and 3, we don't have to worry about anything. But between E3 and E4, E3 minus the work of friction will equal E4. Or E4 will equal any of those. E4 plus the work of friction. We'll deal with friction in a minute. Now, we're going to assume, looking at this, that H1 and H2 are 10 meters and H3 is 0. So let's get rid of H3. Also, we're going to clear the spring. So X1, X2, and X3 are going to be not applicable or 0. So we can get rid of these guys. Okay. K is 80,000. 80,000 meters. What is our M? 100 kilograms. And what is our X initial? Initially is compressed 40 centimeters, so negative 0.40 meters. All right, that is our initial, and our V initial, or our V1, is going to be 0 meters per second. We don't know what V2 is, and we don't know what V3 is. So let's make this 2, 3, H1, 2, H1. So what we have is, and then this is 30 degrees, and mu is 1.3. We'll come back to that. 0.13, whoops. We'll come back to this eventually. So first things first, what is the student's speed at 2? So mgh1 plus kx1 squared over 2 is equal to mgh2 plus mv2 squared over 2. However, h1 and h2 are both 10. So we can make those go away. We don't need those. And the spring energy all turns into kinetic energy once they're released. Okay. So V2 is equal to multiply by 2 over m, and then take the square root, k over m x1 squared, which was 80,000 divided by 100 times 40 centimeters squared. This is 800 times 0.4 times 0.4, square root of that answer, is 11.3 meters per second, or 11, okay? Now, how far up the incline do they go? Now, we could come back here and figure out what the speed is at 3. We could set mgh2 plus mv2 squared over 2 is equal to mgh3 plus mv3 squared over 2. And then say, well, this is 0 because at the bottom at 3, h is 0. And we could find that pretty easily. It would turn out that v3 would be the square root of 2gh2 plus v2 squared. But we're not asked for that. What we are asked to do is to find how far up the incline does the student go. And this is a little weird, okay? It's a little hard because I don't know what they mean by how far up. Do they mean the height or do they mean along the incline? I'm going to assume they mean along the incline. Okay, so the energy at 4 is mgh4 plus mv4 squared over 2 plus kx4 squared over 2 plus, and energy 3 is equal to energy 4 plus work of friction. The work of friction is mu mg cos theta times x. So note, as we slide up this ramp, our normal force is mg cosine theta. And the distance we travel is x, okay? Now, let me actually back up for a minute. We're going to slide to a stop, so V4 will be 0 when we slide to a stop, and we have no spring, okay? So the energy at 4 is going to be mgh4. However, if I want to find how far up that is, okay, if this is h4, well, then the distance that you slid up, h4 is x times sine of theta, or we can just change this to mgx sine theta. Okay, the reason why we're going to do that is you'll see that we need things in terms of x. So E1 is equal to E2 is equal to E3, but E3 minus work of friction is equal to E4, or E3 is equal to E4 plus the work of friction. So I'm going to write it as E4 plus the work of friction. And since I already know what, well, I'm going to have to figure out what that is. I'm going to use the following. Let E1 equal E4 plus the work of friction. I'm going to write that up here. So mgh1 plus kx1 squared over 2, that's energy 1, is equal to mgh4 plus mu mg cos theta times x. We're going to rewrite this on the next page. mgh1, energy 1, is equal to energy 4 plus work of friction. Energy 4 was mgh4, but remember h4 is x sine theta, mgx sine theta plus mu mg cos theta times x. Now let's rewrite this. mgh1 plus kx1 squared over 2 is equal to x times mg sine theta plus mu mg cos theta, or how far up it went is mgh1 plus kx1 squared over 2 over mg sine theta plus mu mg cos theta. And m was what? 100. So this is 100 times 9.8. Height 1 was 10. K was 80,000 plus 80,000 divided by 2 times 0.4 squared. It was compressed 40 centimeters divided by 100 times 9.8 times sine of 30, right? Yeah. Plus 1.13 times 100 times 9.8 times cos of 30. So I get 100 times 9.8 times 10 plus 40,000 times 0.4 times 0.4 divided by 100 times 9.8 times sine of 30 plus 0.13 times 100 times 9.8 times cos of 30. I get 26.98 or 27 meters. Okay. But the main takeaway here is, here it had spring energy and potential energy of gravity. The student initially is at a height, so it has a potential energy of mgh and spring energy of kx squared over 2, where x is the 40 centimeters, 0.4 meters. Then they slide past the spring. All the spring energy becomes kinetic energy, so they still have mgh, but now instead of spring energy, they have kinetic energy, mv squared over 2. They slide down, then they slide up. So whatever energy they have at the bottom, which is the same as the energy they have at the top, it's just now it's all kinetic energy at the bottom, and you could find that if you wanted. As they start to go up, they start to lose energy, not just to friction, which is mu mg cosine times the distance along, but also they're gaining potential energy, mgh. So their final energy is going to be mgh, but they're also going to lose a certain amount. And you had to turn h into x so that you could solve for the distance up. And that's what we did here. We wrote mgh plus kx squared over 2 for the energy initially is equal to mgy, where y is the distance up the incline times sine, plus the work of friction, which is mu mg cosine. This is mu n. This is mu, and this is n, but n on a incline is mg cosine. So mu n times x up the cosine, up the slope. And setting those two things equal and solving for x gave us 27. Anyway, our final problem of this is, it's your birthday, you're going to jump off a bridge with a bungee cord. So we need to be very careful. I talked about this in class, but we have to be very careful about certain things here. You're going to jump off, you're going to assume that your mass is 80 kilograms. And the bridge is 120 meters above the water. So this is 120 meters. The 30-meter long bungee cord, so when it's at a height of 90 meters, this thing is at its equilibrium. Once it starts to go below that, it's going to pull back. So we're going to define x downward is positive and X upward is negative, doesn't matter, but we want to know how far are you when it reaches its maximum elongation. Okay, so here's the deal. You're going to fall from rest. So we're going to have 1, 2, and 3, although we don't really need to worry about 1. We'll talk about it, but I guess we kind of do need to worry about 1. But we're going to assume that you have no spring energy up there. Okay. Now, you do have potential energy at 1. So your energy at 1 and your energy at 2 and your energy at 3 are mgh plus mv squared over 2 plus kx squared over 2 for all of these. Turn your brain off and just write down the 3 types of energy. And then slowly work your way through each one. All right. Now, just thinking about this, at 1, you have no kinetic energy. You're falling from rest, and the bungee cord doesn't start working until you get past this point right here. At 2, you should have all, well, you won't have spring. At 2, you'll have mgh and mv squared. And then at 3, well, we're going to assume that 3 is somehow before you hit the ground. So 3 is somewhere. You're not going to have any kinetic energy anymore, but you'll still have mgh. So let's start by setting. We're going to set y is 0 here. Okay. And then we're going to say that y is 30 meters up here, so that y and x are the same. It doesn't matter whether this is positive or negative, so I'm going to call this negative, call this positive. Okay, and then we're going to end up with y is something here. All right. Now, what we want to know is how far are you above the water when the cord reaches its maximum elongation. So we can set E1 equal to E3. And what we get is mgh1 is equal to mgh3 plus kx3 squared over 2. But x3 is h3. Let x3 equal h3 here. All right, so what we get is mgh1 is equal to mg, and I'm just going to call them x plus kx squared over 2. And we need to solve for x. h1 is 30 meters. X is, sorry, m is 80 kilograms. K is 48. And finally, nope. Okay, so we need to solve this for x. Now this is a quadratic. So if I rewrite this as kx squared over 2 plus mgx minus mgh1, set that equal to 0. My a is k over 2. My b is mg, and I'll put numbers with these. And my c is negative mgh1. So k over 2 is 48. 48 divided by 2, or 24. B is 80 times 9.8, or 784. And C is negative 80 times 9.8 times 30. So times 30 is negative 23,520. Okay. Um, in order to make this a little bit easier, I'm going to do something a little weird. I'm going to divide through by mg. So if I do that, what I'm going to get is that my A is now the following. And if I divide this side by mg, it doesn't matter because I have 0. Okay. So I have negative, B is 1, and this is K over 2 mg. So this is 48 divided by 2 times 80 minus 9.8. This is 0.0306. B is 1 and C is negative 30. Now, negative B plus or minus B squared minus 4AC over 2A. This is negative 1 plus or minus 1 minus 4 times 0.0306 times negative 30. So this becomes a plus, and 2 times 0.0306. All right. 1 plus 4 times 0.0306 times 30. 4 times 0.0306 times 30 plus 1. Square root of this answer. So this is negative 1 plus or minus 2.16 over 0.0612. All right. But do I want positive or negative? Well, I want X to be negative. The reason why I want it to be negative is because I'm falling. So my negative, I'm going to get, I'm going to add the negative. So negative 3.16 divided by 0.0612. And I get negative 51.6 meters. All right. So coming back to here, I get negative 51.6 meters. That is where energy 3 is. Now, keep this in mind. I want the height above the water, though. So this was 30 plus 51.6. So 120 minus 30 minus 51.6 is 120 minus 30 minus 51.6 is 38.4 meters. Because that's what they asked me for, or 38 meters. Okay. This thing is a bit of a pain the way they did it. They chose to do it by setting up all of these relative to y initial being the bottom, and you can certainly do that. I, on the other hand, set it up so that my energy at the top was mgh, and my energy at the middle was mv squared over 2 plus mgh2, and my energy at the bottom was mgh3. This was where the spring first started, plus kx3 squared over 2. And then I had to figure out, okay, how do I relate all these things so that I can solve it? And my first step would be set this to 0. Let x be 0 here, because it is. This is where the spring started. And I knew that this was 30 meters down. It told me that the bungee cord didn't start stretching until 30 meters. And so this x3 is going to equal h3, and they're going to be negative. They're going to be down and negative. They have to be, because mgh, we assume that mg is down and y is positive up. And that means that h1 is 30 meters, but I don't know this. And by setting these two things equal, mgh1 is equal to mgx plus k over 2 x squared. I can solve this for x using a quadratic. To make my life simpler, I can divide through by mg, and then it becomes a quadratic that is k over 2mg times my x squared plus 1 times my x minus h1. This is my A, this is my B, this is my C. Once I've done that, once I've found my x, and I have to choose the negative, I know it's going to be the negative. Once I've found my x, I have to rescale it from y is equal to 0. And I have to figure out where, if at the bottom is 120, then I have to figure out how far above, because that's what they asked me for. And that's it. It's a tough problem. It's not easy. But if you can do it, great, you've got this. However, this is how they did it. If you want to pause the video, we'll go through this and see. It's how they did it, essentially, with big numbers. It's kind of a pain because the way they did it, they set everything to, I believe, either the top or the bottom. Looking at it, it looks like they're solving it for h minus L, where I solved it for x. Anyway, so hopefully this helps. Just remember, energy is pretty simple. As a quick, just a quick review of energy concepts, work is F dot D, which is mv final squared over 2 minus mv initial squared over 2. The work of gravity is the minus potential energy of gravity, which is mgh initial minus mgh final, and that means that you have to choose y up and the force of gravity mg down. The work of a spring is the minus potential energy of the spring, which is kx initial squared over 2 minus kx final squared over 2. And then finally, that gives us that the energy at any time, you can simply write as mv squared over 2 plus mgh plus kx squared over 2. And you can set, as long as there's no non-conservative, read friction, forces, you can set the energies equal, they're conserved. So you can just write this down and pick a couple points and set those energies equal. If they're not attached to the spring and they leave the spring at some point, they won't have spring energy anymore. And you choose where the height is 0. We've done that a bunch. The last thing is the normal force is mg for a horizontal surface and mg cosine for an incline. The work of friction is mu n times d, however far it slides. And if there's a region with some friction, then the energy 3 minus the work of friction is the energy at 4. So you're sliding through there. Or the energy at 3 is the energy at 4 plus the work of friction. And the reason why we write it this way is, let's say it came down a hill where it had some other stuff happening at 1 and 2. You could say that energy 1 is energy 2 is energy 3 is energy 4 plus work of friction. You can't do that here. This would have to be energy 1 minus work of friction is equal to energy 2 minus work of friction is equal to energy 3 minus work of friction is equal to energy 4. It's actually easier to conceptualize it, I think, this way. But essentially, that's everything that you need to know. Make sure you remember how to do the dot product. And then all these problems were just understanding how to put together work and energy in various ways. So anyway, I hope I'll see you tomorrow. See you soon. Bye.